Okay. Howdy, everyone. Hope you're having an amazing week so far. Today, we have Henry here with us, and he is a Google developer expert in machine learning. And he will be conducting a workshop on TensorFlow. So, without much further ado, Henry, take it away.
Okay, welcome guys. I am so excited to be here. So thank you for having me to have the opportunity to share with you guys about, in this case, about TensorFlow. And okay, I'm gonna start talking about what are the topics that we're gonna discuss today, and then I'm going to share with you guys on GitHub when you can go and access to the notebooks and all the code that we're going to discuss today. So I'm going to share in the chat, let me, a GitHub repository, so you can go right now and access to the code, and we're gonna try to access them later using Collab. I'm going to discuss what Collab is and everything. So you guys can, for now, just check it out, that repo. Okay, so I'm Henry Ruiz. I'm Google developer expert in machine learning, also PhD student, Texas A&M. And first, I'm gonna talk a little bit about what Google developer experts are. So if you guys want to get more information about, and if you want in the future apply or something, so you can go to this link and you can get more information about how this works. This is like, in this case, a Google, you need to be nominated for a Google developer expert or for someone that works in Google. And then you go through like a process of 2 or 3 interviews for people in Google. And then this is basically the process. And this itinerary process is very similar to how the developer student clubs work when you guys apply for this stuff. So today we're gonna talk about machine learning and deep learning. So this is what we have today for the agenda. So I'm gonna start talking about what is machine learning and what is deep learning, because it's very easy to get confused with these terms. So I'm gonna try to go through them fast, and then we're gonna move to the code, which is basically probably why you guys are here. I'm gonna make a brief introduction about neural networks. It's very short. I want to go in the math details because we don't have the time to do it. So it's more to you guys learn the intuition behind of these algorithms. So we're gonna discuss what a deep learning framework you have. And then I'm gonna start talking about TensorFlow. And finally, I'm gonna discuss, if we have time, about some open source project that I have been working on. And it's because I would like to give you an invitation if you want to be involved in these projects. So this is one of the reasons. This is one of the reasons why I don't want to talk about math stuff here. We're gonna start just talking about how implement all of these algorithms that we're gonna discuss today. So I encourage you guys to find this post about why we should avoid equation in this kind of talks. This is a really good post about that. Okay, so first I'm gonna talk briefly about what is artificial intelligence, what is machine learning, deep learning, and the difference between them. So this is very important to have clear what is the difference between these areas. And one of the reasons why I say that is because it's very easy to overwhelm with all of this information in internet. So when you start looking for what is machine learning or what is deep learning or this stuff, you can find a lot of information and you don't know exactly where to use to start. So I'm gonna start talking about what is artificial intelligence. Artificial intelligence is an area of computer science focused specifically in the development of algorithms or models that somehow they look for like a way to try to mimic some human behavior, some natural behaviors into a machine or into a software. So one example of that, there is a really good paper. I'm going to share with you guys all the resources that I'm going to mention. So about some people in MIT working to try to observe how the ants work, how they organize the colony, how they make decision together and this kind of stuff. And they are trying to replicate this kind of behaviors to see if using those kind of natural phenomenons, they can improve and optimize the how, like in this case, how in the networks we share information. So it's really, really, really good paper to read. And in artificial intelligence, it's not only machine learning and deep learning, there is other stuff like optimization, genetic algorithms, computer vision, speech recognition. So there is a huge area of research in the computer science side. And machine learning is just a subdiscipline or just a part of that. And so in this case, machine learning is focused on how I can use information on data that I have been collecting in different ways to do predictions. And we're gonna see how this works more in details later in the presentation. And neural network is a way of machine learning. So these kind of models or these kind of algorithms are called bioinspired, and mainly because these kind of methods are based on how our brain works. It's not actually how our brains exactly take decision or this kind of stuff, but they just like take some concepts and try to apply this into these kind of models. And we're gonna see this more in detail. So if we want to do a definition about what actually machine learning is, so we have two definitions here. One is, I'm gonna put this here. Okay, so I put here two definitions. One from a general perspective. So this machine learning is a discipline focused on how to build systems that automatically improve according to their experience without being programmed for it. And when we talk about experience in terms of software, is just the data that these kind of systems are collecting every single day. So you know that we have a software that this software have a database, and we all the time are like collecting information. How we can use that information to make the software or the machines autonomous to take decisions. And from a specific and more technical oriented definition, consists in training a machine learning or a mathematical or a statistical model using historical information to infer or predict the value of a variable. And this is very important. The main goal of machine learning is use the data to make predictions. And this prediction, in this case, we want to predict a variable, and this variable can be a discrete variable or can be a continuous variable. And this is really, really important because this is actually which defines what kind of problem we are facing. So, and this is what we are talking about. So if the model that I implement, the model that I need to train is to predict, for instance, the stock price of the most important companies, software companies in United States. So in this case, we can see that this variable is continuous. So that means that we are facing a regression problem. We want to train a regression model to do this kind of predictions. But if the output of our model, in this case, is a discrete variables, what we're gonna do is train a classification model. So this is very important. Based on the nature of the variable that we're going to predict, we know if we are talking about a regression or a classification problem. And how actually these algorithms learn. So depending on the problem that we are facing, so we have something that is called unsupervised learning. supervised learning, and reinforcement learning. How the models, the unsupervised learning model works. So we basically just give the data to the model, and the model going to try to find somehow using different kind of mathematical approaches and statistical approaches to find we have our data set, and our data set have multiple observations. So what the model going to try to see is if there is any relationship between those observations. Just to put an example, imagine that we have all the students in Texas A&M. So what kind of feature I can use to group them, to cluster them, to like identify patterns in the different groups. So this is unsupervised learning. But supervised learning is almost like when we grow, you know, when we are children, we just, our moms say, okay, this is a cat, this is a dog, and your mom teach you, this is a dog. And then internally, you don't know, but your brain start like extracting information, extracting like recognizing, you know, some color, some shapes in the objects that you see around. And then later, when you see that object, you are able to identify them. And this is how supervised learning works. You have a model, you give you examples to that model, and the model going to learn from them to do predictions. And this is just think about like a baby. Our model is a baby, and we try to teach how to like recognize objects, recognize things, or this kind of stuff. And there is another way how these algorithms learn, which is reinforcement learning. And this is actually more similar to the way how we learn, because you know that hormones always saying you don't, please don't do this, please don't do that, but we are still like going and doing the kind of stuff. So we basically learn from our experience, even know that we can do some stuff, even know that we can do some things. We go to the world and we, you know, we finish doing this stuff and we learn from our experience. So how reinforcement learning works, you have an artificial agent into an environment, and this agent use all the information available in this world to make decisions. But the agent itself going to like figure out how to do the task that we want that the agent do. And this is very important because we have an artificial agent into an environment, and we need to define a set of policies that, and this kind of policies is the rules that this agent going to follow to take decisions. And this is just an animation how you probably help to understand these concepts. So we can see here classification, you can see clustering, group the observation based on some features, and this is reinforcement learning. You can see that you try one time, then one more time, and this generation by generation you are learning and learning and learning. This is it's funny. And there are different algorithms that you can use according to the problem that you are like trying to solve, and according to the learning method that you're going to use. So this just gives us some examples. So we have a problem and we're going to train a model. This model could be a classification or regression problem. We are talking about supervised learning. And this is some of the most common algorithms to use for this kind of tasks. So we won't go in details and talk about them because it's very technical stuff, but you can just have an idea what kind of algorithms you can use to solve a specific problem based on the constraints that you have. And there are, when you have your data, your observations, or before to start talking about data, just imagine that somebody hired you guys to develop an application that classify flowers. So you have two different ways to approach that problem. One is using feature engineering, and And the feature engineering means use the traditional methods, which is the method that I mentioned before. And how this works is like you have an observation and you need to define what kind of feature you can extract from the observation to do the task. So in this case, I had a picture of the flowers. So what I do is basically visually try to identify what feature I can use to do the classification. What kind of feature I can use to maximize the difference between the classes that I have. In this case, I have 3 different classes: versicolor, setosa, and virginica. So after doing like a visual inspection, probably with the help with an expert in the field, so I identified that using the petal length and the sepal length and also the width and the height. So with those features are enough to do the classification or to do the differentiation between the classes. So then I just basically train my model. I just extract manually, or I can use image processing to extract the features. And then I create a CSV file where each row corresponds to an observation. So an observation is just think about like an example. And then in the last column, I specify the class. And I use this CSV file to train a classification model. So just to make a recall, here we need to have defined the features. We need to have clear the feature that we're going to use. But sometimes it's really hard to extract those features. So because it's costly or because our problem is very abstract and it's not easy at all to try to extract those features. Just think about, I have a friend that she is working developing a model to identify if some genetic information in the cows and relationship between the milk productions. So these kind of features are really hard to find. So in this case, we can use deep learning. So deep learning is mainly used to process unstructured data. So that's mean that images, audio files, to do speech recognition, or this stuff. And what is the difference between deep learning and the previous approach, feature engineering? In this case, we use neuronal network. And what this neuronal network does are they internally extract the features. That means that we don't need to have clear the features because the model itself going to figure out which are the features that the model need to do the prediction. So just talking about the previous, just talking about the flowers example that we're talking about. So we have a neuronal network here. This is a set of layers, a stack. And in each layer, I stack different features, applying something that are called convolutions. And in each convolution, what I do is I take the image and I pass this image through a processing pipeline, and I extract a feature like the borders. You can see here the kind of information that we're going to extract in each of those layers. Okay, and when I have those features, then the next step is do the predictions. So it's actually I can use this kind of convolutions to extract the feature. I use a model like what we discussed previously to do inference. Okay. So machine learning is a huge area. So you don't need to be a mathematician, or you don't need to be an statist and someone with a statistical background or like. But it's good to have this kind of knowledge because it's going to help you to, to understand how this model works. But there are different tools out there that you can use it. And here are all the tools that are available in different knowledge levels. So if you guys are developers and you just want to just include this information, just include this kind of deep learning models or this kind of solutions in your software, you can use APIs. I know that you guys discussed in the previous section about how to interact with APIs. So you can just use the Google Cloud Platform and use the custom vision API or use the speech recognition API and it's done. So this is all the kind of solution that we have at high level. We have the Azure Cloud, we have Google Cloud, we have IBM Watson, and all of those cloud solutions already have all of these algorithms implemented. So you just need to you just need to use the APIs and that's it. But if you want to go more in the research and if you want to go more in the detail of the implementation of this kind of stuff, you can start exploring other kind of tools. For instance, TensorFlow, PyTorch, Keras, Fast API. So it's depend of what you guys want to do and how deep you want to like swim into this ocean. You know, like we have a different bunch of tools and you can just decide what kind of tool. And this is very important in terms of architecture, because when you are like developers, you need to have the skills to take the best decision for the company for like where you are working. So sometimes you have the time to and the budget to create a group to work in like custom solution, but sometimes you don't have it. So you need to go for more high level solutions like Google Cloud and stuff. And in this talk, we're gonna focus specifically, before to pass to the demo part, in parametricized learning, which is how the neural network works. So how the neural network works, so we have the data, and our model have something that is called a score function. This score function is going to tell to the model if the prediction were good or not. And we have a loss function. A loss function going to allow us to quantize the error. So how much wrong is the model? So, and we have some parameters that the model going to learn, which is this is actually the magic behind of this kind of model. The model itself going to learn these parameters. And how this happens? This happens using some optimization algorithms. Okay, so this is all the components that our neural network is going to have. And this is why this is called, why this kind of model are called bio-inspired models, because this is here is an animation about how the synapses happens in our brain. Synapses is the process that when like 2, 3, or like a set of neurons interchange information between them. And you can see how they are activated. So every decision that we make with our bodies, you know, to just touch something, to kiss somebody, whatever we do. So all of these kind of decisions are because there are some things that are happening in our brain, and this is how it looks like. We have this kind of set of layer or a structure that. And this is the same what's happening with neural network. We have a set of, we have different layers. This layer is going to extract different information and different levels. And we're going to use that information to do predictions. And we're gonna have an input and something going to happen in the neurons. This is talking about artificial neurons, and we're gonna get the output, which is the predictions. And before to start talking about more complex architecture, it's important to highlight that when we talk about machine learning, we talk about models. When we talk about deep learning, we talk about architectures. Why architecture? Because it's how we stack different layers in the way that we can solve a problem. This problem can be a classification, image classification problem. This can be a speech recognition problem or something like that. So, and we're gonna talk with the more simple architecture. We see the perceptron, and this is what's happened. So we have our data. Each observation of data, just think about that. Our data is a matrix of columns and rows. The columns are the fixtures. The fixtures can be the age, the sex of the person, can be, for instance, any kind of fixture that we can extract from our observation. Of each observation, just imagine that it's a person or something like that. It's basically the source from where we extract the fixtures. And each observation can be represented as a vector. So we can actually plot it, you see? So, and why? It's because even knowing that our data set can be multidimensional, what that means that can be multidimensional, that we can have more than 1, 2, 3, 5, 6, 7 fixtures. We can somehow represent this observation in 2 or 3 dimensions. There are some algorithms when you have a 7, 8, 9, 10 fixtures, and you can do some dimensionality reduction, and you can convert these n-dimensional vectors into 2D or 3D, and we can visualize in this way. We're gonna see how. And when we visualize our data, we can notice that our data can be linear separable or non-linear separable. So we can see that here we can just use a linear function to define the hyperplan that separate the 2 clusters of data. Just think about that this is people that have diabetes and this is people that don't have diabetes. And we can, with a linear function, classify them. But there are some more sophisticated problems where we don't have this option. And this is how the perceptron works. The perceptron works in the way that you have a multiple inputs. Each input have a weight. What this weight means is how much that particular fixture influence in the prediction. So just think about it that we want to predict if a person have cancer or not based on some fixture like the age, if that person had family members that have cancer before or something like that. So what the model going to do is trying to identify which of those fixtures that I defined had more impact into the output. And this is given by a weight. The weight going to say this fixture is more important than the other one. And what's happened here in the neuron, so if we do a zoom, is we take those weights, we multiply those weights for our inputs, and we zoom a parameter that is bias, that for this, for teaching, in this case, we don't going to like talk so much about bias, but bias is like a parameter that helps us to adjust that linear function. And then, so based on the result that we got from this neuron, so if the result is greater than 1, so we're gonna say that the person have cancer. If the output is less than 1, so that's mean that the person doesn't have cancer. And this is how that works. And we basically just think about here, this example, we need to train a classifier to classify cats and dogs. And we start playing around with those parameters, with those weights, to identify what is the linear function that separates these 2 clusters of data. So we can do this manually. So that means that start changing the weights arbitrarily, or we can use an optimization algorithm, which is how the neural network works. And how multi-layer perceptron works. Multi-layer perceptron is a solution for problems where the data is not linear separable. And how that works is like you actually have multiples perceptrons and you stack them. And then we don't have right now one only linear function. Instead, we have multiple of them. And then we're gonna create a hyperplane based on these linear functions. I don't go in more. I think that I'm gonna stop here so you can later go into the presentation. I go into directly to the demos. But before, I want to show you some visualization that are going to help you guys understand better how this works. This is a really cool visualization tool. Just think about that this is our data. You can see that our data here is easily separable with a line function, right? So, and we know that a perceptron is only one neuron, and our output going to be cancer or no cancer, for instance. Imagine that this is the cluster that corresponds to the people that had cancer, and this is the cluster that the people that correspond. And I want to implement a perceptron that help me to do this classification task. So I defined what is the activation function. The activation function is what I mentioned before. So what's happening in the neuron is like you have your inputs and you multiply the input for the weights, and then you apply an activation function. The activation function is basically the function that say that if this neuron should be activated or this neuron shouldn't be activated. Okay, this is in simple words. And then I'm going to train, and you're gonna say that it's very easy for a perceptron to find the solution here. But what happens if my data is like that? So I cannot use a linear function here too. And if I try to use a perceptron here, the perceptron going to try very hard to find a linear function to separate those clusters, but this is gonna be impossible. So then here is when we start implementing more sophisticated architecture. So then I start saying, okay, let's see what happens if I add 4 neuron more. So I just run it. And you can see that now the models start like a learning. And now we don't have, let's see, maybe we can add some. Let me run here. And you're gonna see that eventually when I start stacking more and more and more layers. So you see that it's basically like combine multiple linear functions to find the solution for a nonlinear problem. This is very awesome. It's just like, you just think about that you use this function in this, you see that this function is here, 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 and you merge them, and then you find the solution for like this problem. So this is a very cool solution that you can explore more in details. You can interact with different activation functions, do some different kind of stuff here. So I encourage you guys to do that. And what happens when you are working with images? When you are working with images, so there are some layers that are focused specifically in extract the features from these images. So for that, we have some layers that are called convolutions, and this convolution, what this kind of operation do is try to find this kind of patterns. You see, like you have a, let me see. You have a kernel, a window, and you slide that window through your image. And this kernel have some weights here. And then when you apply this weight into your image, you can highlight the borders, you can highlight the, and this is the feature, this is kind of the feature that the model is going to use to do prediction. Okay, so this is, I don't want to talk more about the theoretic stuff. I'm gonna go directly to the examples. And for that, I encourage you guys to go to Colab. You go into Google and put here Colab, please search google.com. I don't know if you guys can see it. So okay, so probably this is the link that you guys need to go. Colab. I'm actually going to send this link in the chat. I think that is
I already sent it in the chat. You're good.
Okay. Yeah. So you're gonna go there, and then we're gonna start with the basic implementation of the perceptron. Then we're gonna go and see a multi-layer perceptron to work with structured data, and then we're gonna see an example of convolutional neural network. So probably we won't have enough time to go through all of them, but at least you guys have the code, and the code you can just follow after the section. And here you can go to the GitHub, And I give you guys the link of the repository. I give you guys the, is this one? Probably you already have it. Just enter. And you're gonna see that here there are multiple notebooks. We're gonna start here in the perceptron. Okay. And here it is, our basic perceptron implementation. So first, okay, I don't know if you guys already know Python. This is a Python implementation. TensorFlow also have some wrappers that you can use in other kind of languages. So we start like importing TensorFlow. We're gonna use the Skylar library, which is another library very known in machine learning in Python. So in this case, we're gonna use it for work with one of the data set that is already included in that library. We're gonna use matplotlib to do visualization, and we're gonna use NumPy for like some matrix operations. So you're just gonna control enter to execute that particular cell, and we're gonna say here run anyway. And we're gonna wait. Okay, so we have now the imports here. So we can check the version of TensorFlow like that. Look at how we import TensorFlow. Import TensorFlow, this is the name of the package, as TF. This is an alias. This is like a short name that we are assigned to that particular. Okay, this is the version. And what we start doing here is generating data. So since we don't have any kind of data set, we're gonna use a data set from Skylar that is called blobs. Then we're gonna say make blobs. I'm going to say I want to generate 50,000 observations. Just think about that there is 15,000 persons that have cancer, or 50,000 persons that, you know, any kind of stuff that you want to like. I say 2 centers because you see that I have two clusters here. If I say 3, so what's gonna happen also. So instead to create 2 clusters, I'm going to create 3. I'm gonna just say 2 because we're going to explore how the perceptron works, okay? And the perceptron, remember the perceptron is only for binary classification and also for linear problems, for problems with our linear separables. And we're gonna say that we only have 2 fixtures. That's it. And what this function going to return, this function going to return the fixtures. I'm gonna comment out this. I'm going to print the fixtures shape. The fixture shape is just a matrix of 50,000 by 2 because I have 2 columns. Remember that you can have multiple fixtures. And the labels. And if I see the labels, you're gonna see that just the labels are 0 and 1s. 0, that means that belong to one class and 1 belongs to the other. So this is why I here say 1 and 0s. And if I actually print the shape of labels, you guys are going to see that it's just a vector, okay? But in order to like pass this to our models, we need to do some transformation to our labels vector, and we're gonna convert this into, we're gonna basically do the transpose. If we print here labels shape, you see that now I have 50,000 rows and 1 column. This is I just make that vector into a column representation. And I just plot my data. I just say I want to plot the fixture 0 and the fixture 1 because I know all the rows, fixture 1, all the rows, column 1, you know, so that means that I have vector 1, vector 2, my vector 1 going to be X and my vector 2 going to be Y. And who's going to give me the class or the color of the clusters? So the labels, okay? This is pretty easy. We have that, perfect. So now we need to define our model, and we know that since we are talking about linear functions, so if you guys remember in linear algebra, so a linear function is defined based on this equation, right? So we have our input x, which is gonna be the value of our fixture, and we're going to try to find a and b. B is the bias, which is an adjust parameter. We're gonna see how these parameters affect the linear function, and a is the weight, okay? So if you can see here, if I modify this, the bias, this is what happened. So the bias kind of control the location of the line, and this control the direction, you see? So then I can start doing that manually until I find the function, but we're gonna train a model to do this by yourself because, well, computer science, you know, we are lazy and we want that the computer do everything for us. So we're gonna create, in this case, two variables. And in this case, we are not talking about Python variable itself. We are talking about TensorFlow variables. And this is what we need to do. And one of the reasons is because what TensorFlow is doing internally is creating a computational graph. What does a computational graph means? If I come to the presentation for a moment, I'm gonna try to show you this. One of the reasons TensorFlow is called TensorFlow is because we have a tensor, and this tensor can be a multidimensional array or just an scalar value. You know, depending on the kind of dimension that our data, we used to represent our data in a matrix way, right? Columns and rows. But we saw that for images, we need more dimensions because we have an image, and an image is basically a digital representation of color, where we have a red matrix, green matrix, and blue matrix that represent that particular color. So the reason why this is called TensorFlow is because we have a tensors, and this tensor is going to pass through a computational graph. And why TensorFlow create this graph is because this is going to allow TensorFlow optimize the way how is executed. Because we're going to run our models into the GPU, into the TPU, into like, you know, so then TensorFlow need to have the option to like take those kind of different nodes and say, I want to run this operation in one of the core of the GPU. I want to run this operation in other core of the GPU. So this is why TensorFlow is represented like that, or models. And also because TensorFlow need to have the way to compute the gradients, because the gradients going to say to the models if the model is good or if the model is bad, or we're gonna talk more about that later. Okay, so we have two variables. We are basically creating two nodes in this computational graph that I show you guys. And I say, okay, this is a variable. I'm going to initialize those weights in this form. You say that if I print W shape, you guys going to notice that we only have two values. And why? It's because we have two fixtures and we need to find two weights, okay? And we can initialize those weights with 0 values, or we can use random uniform distribution or whatever. There are different ways. When we initialize those weights as 0, we are basically saying that we're gonna start assuming that these two variables that I consider in my model doesn't have any kind of relationship with the output. So then the model is going to try to find that kind of. So I'm gonna create my W and my B variables, And let's see if we just initialize the weights and the bias. We have not doing any kind of learning at all. So let's see what's happening if I use these random initialization variables to visualize or model how do the prediction. You see that the prediction is pretty bad, right? So this is what we expected. So we can continue going, and so that's mean, and this is how we actually compute the loss. This is another important function in the neural network. We need to have a way to compute the loss to quantize how grown is our model. And the way that how we do that is we basically take the difference between the labels. The labels is the information that we already know. We know the classes of the examples and the prediction that the model did. And we take the difference between them. This metric is called the mean square error. So this is a very common function to compute the loss. We just take the square difference between the labels. We see the value that we expect to get and the prediction that the model do. If this value is so high, it's because there is a high difference between them. So that means that the prediction are wrong because you expected that this value will be almost zero because the prediction should be pretty similar to the real values, okay? And here is where we define our perceptron. We need, what I mentioned before in the slides, we need a score function. This score function is going to do the prediction, and how the prediction works in a linear model is just following this formula here. A multiplied by X plus B. And this is exactly what I have here. The multiplication of the fixtures by the weights plus the bias. And these two parameters here are unknown for us. So the model is going to learn them. We need to have the loss function. The loss function, we already know that the loss function is going to tell us in each epoch, in each iteration of the training process, how grown is our model. And then we have a learn function. This is actually where the magic happened. So we're going to run this function m times. In this case, m times means that I can run this function 500 times, 1200 times, forever. So depending on the number of epochs that I defined. And what I'm gonna do is I'm going to get the examples. I'm going to do the prediction of these examples. I'm going to compute the loss based on the predictions and the real values. And then I'm going to get the gradient. Because the gradients are going to tell me, so the rate of the change based on those parameters. And based on that, I update the parameters. I update the parameters in my model. Okay, and I return the loss. And I do the same n epochs. So you see that I define that the number of epochs going to be 20. So for each epoch, I'm going to take one set of observation in my data set. I'm going to learn and I'm going to get the loss. And in each iteration, I'm going to update the two parameters. So here is where we actually are learning our waves and our bias parameters. And when I run this, so the model going to start learning, you're gonna see that eventually it's going to stop in the epoch 20. And you see that it's doing a very good job doing the predictions. And I include some function here to compute something that is called the plot decision boundary, which is define the area of each cluster. So I want to show you guys another more sophisticated example before to finish, but I don't have so much time. So I think that probably in the future we can organize a more like a detailed workshop or something like that, where we can go in detail through each topic or something like that. But all of this code that I did almost step by step using TensorFlow high-level API is just these 3 lines of code. So I say, okay, I have my model. My model is a sequential model. Why is a sequential model? Is because I have a stack of layers. So I can just think about that. It's like an array, and each position of array going to be a layer. And here I add only 1 layer, and this layer have only 1 unit, because if we are talking about 1 perceptron, if we want to add more layers, we can say 5. And what we are doing there is basically something like that. We are saying to TensorFlow that we have 2 inputs, and we only have one layer. This is of layers, and we have only 1 unit. If I say here, instead to say 1 unit, I say 2 or 3. So is in this architecture, I start adding more nodes. And why this kind of layers are called dense is because my inputs are connected to each node in the next layer. This is why this kind of layers are called fully connected layers. And I'm gonna get outputs, and my output going to be if the person have cancer or not have cancer. And what the model going to learn? The model going to learn the way of these variables, x1, respect to this linear function, going to learn the way respect to this linear function, and going to wait respect to this linear function. And the same happened for the other neuron. Okay. Yeah, so you can see here is just 2 lines of code. We say that this is the kind of optimizer that we're gonna use, and this is the loss function, the mean square error. We already know how to work. It's just the difference between the real prediction, the prediction with the values, so the real values. Just think about that you have a subset of cats, and you have a trained data set. In this data set, you have all the features of the cats, and in the last column, you have this is a cat, this is a dog, and you get the difference between that column to the predictions. And you expected that this difference will be close to 0. Okay. And here you can actually, I can do that. And here I define my model. I say I want to train my model by 10 epochs. And this is the result. And TensorFlow has some functions to plot the model, and you can actually see here what I am talking about. So how many layers, input layers, or things like that. Okay, this is a basic examples, and I'm gonna go fast in 2 minutes through the other example, which is using images. And I think that I finished. So I was thinking to show some more stuff in the presentation, but I think that we don't have enough time. So I'm gonna open another notebook here. I copy TensorFlow workshop, GitHub. And I'm going to import this convolutional neural nets. I think that is this one. Okay, so here is the same. We just have import. We have our imports. We load our data. TensorFlow have a library that is called TensorFlow datasets, where they have some already defined dataset that you guys can use to test. And using the load function, you can actually get access to the trained subset, the validation subset, and the test subset. And you can define here, I want to get the 80% of my observation for training. I want to get from the 80 to the 90% for validation, and the 90% for test. Here I just visualize the images. And here is where I actually do some convolution. I use the convolution, and this is what's happened internally. You take the image and you extract different features, representation, different levels. And so here I explain how to do data augmentation. Data augmentation is that you can apply some transformation, like rotate the images too soon to increase the number of the examples that you have. Because sometimes you don't have enough data to train the model, so you can increase the number of examples using data augmentation techniques. And here there is a function that is called prepare, which convert all the images to the size that the model accept. I do shuffle. Shuffle is just randomize the data set. I create batches of data set. When I say batches is in each epoch, depending on the number of examples that you define here in the batch, this is the number of observations that the model is going to use to learn in each epoch. And here I do data augmentation and I return the data set here. I prepare the three data sets, the train data set, the validation data set, and here is how I define the model. Look at that. It's the same that we saw before using dense layer, but there are some previous layers here that are convolution that are going to extract the features. So that means that the convolution is just a few of layers that are focused to extract the features and a multi-layer perceptron. We do the classification. And depending on the kind of task that you are doing, so if you are working with images, if you are working with audio, so you can change this kind of layers that extract the feature. But this is what mostly changed when you define your model, the feature extraction layers. You compile, build, do the summary to see how your model are. You train the model using the fit function, and you can plot here the loss. And finally, you do predictions. And something that is really cool about TensorFlow, coming to the presentation, just to finish, is TensorFlow have the option to export the model to run in the browser using WebGL. WebGL is a technology that allows you to access from the browser to the GPU. So you just train your model, and once you have your model, TensorFlow have some export tools to convert your model to run in the browser, to run in Android devices, in Raspberry Pis, or to run in the cloud. This is depending of what you guys want to do. And there is something that is called TensorFlow Hub, when you can go and find a bunch of different models available already trained that you can use in your implementation. And I think that this is all what I have to say. So what I'm saying, probably in the future, I can talk about TensorFlow in the browser, TensorFlow Lite, or more specific applications. So I don't know if you guys have a questions.
Actually, there is one question in the chat.
Mm-hmm.
So, someone asked that, do you have any skip layer examples?
Do you have any skip layer examples? Skip layer examples. So I don't really know what a skip layer example means, but so in this repository that guys I've shared with you, so you guys going to find here almost everything. So here the basics notebook is about how to start play around with TensorFlow, how to create tensor of 1 dimension, 2 dimensions, 3 dimensions. Here is like what the graph means in TensorFlow. So you can see more information here about what computational graph means, why they are useful, and how you can actually graph them, etc. Automatic differentiate. There are different like kind of examples here, and also there are some examples in TensorFlow JS. For instance, how to convert a TensorFlow Python model into JavaScript. So all of these examples are here in this. Any other question?
All right. I don't think there are any more questions. And great presentation, Henry. Um, I'm sure all of our members really enjoyed listening to this and were able to follow along and learn quite a lot. So,
Yeah, thank you so much, guys. I know that this is a lot of information. So for 1 hour presentation, it's because there are like so theoretical concepts that you guys need to have clear before to start actually coding. But I am welcome anytime you guys going to contact me in Slack or you guys going to contact me in LinkedIn. So I want to like spend 2 minutes. Sorry for the time. There are 3 open source projects that I am working on right now. So you guys are welcome to contribute if you want to participate in those. So CVS Studio is a notation tool. It's a interface to create computer vision datasets. Falcon is to train object detection, classification, and segmentation models. And Region.js is, I think that is actually the most cool. So this one, if you guys are interested on, just let me know. So let me show you this first. So this is TensorFlow JS. It's using TensorFlow in the browser, and you access to the camera, and you can use the movement that you are doing in the camera, and it's just like a movement capture in real time. So you just basically are taking the movement that you are doing from the camera and translate this into a 3D model. This can be useful for video games, for movies. So there are some projects that you guys are welcome to contribute anytime.
awesome. Thank you so much for sharing. And with that, I'm going to say thank you all so much for coming. And thank you, Henry, for joining us today once again.
Thank you.
It's wonderful.
Thank you, guys. Have a good day.
Yes, you too. Bye.
Bye.